Okay, let's get into Lab 5, our last online class, lab meeting of the semester. Hopefully we'll breeze through this one kind of quickly so that you're not spending too much time on it. Or at least not spending too much time listening to me talk. So we have really one goal, and it's to complete our discussion of parametric programming and how to implement it in a programming environment. So we've covered this topic. The idea being we have these fixed value assumptions, and that's a common problem in economics. We are interested in the current demand level for some input fertilizer, and we assume the farmer is a price taker. Well, what's of interest to us is, what if you subsidize the output of the farmer, and so suddenly corn is more valuable, and so you need to know, okay, you implement a subsidy. How does that change the output price for the farmer, and how does that output price change the demand for fertilizer? So those are the kind of things we're talking about. So you're a price taker, and we optimize to find the best choice, but we're interested in how those best choices respond when the economic environment, it could be technical assumptions or market assumptions, when those adjust, how do we generate new analysis or new responses. Okay, so linear programming is not quite. I mean, the standard for economic analysis is elasticity. So if you had an idea of what the policy incidence was, how much a 1 unit change in a subsidy or a 1% change in a subsidy impacts the market price, that would be something like a price flexibility. And then you might have an elasticity, sort of an expansion elasticity, that tells you when the output price of corn goes up by so much, then you require so much demand or so much extra fertilizer. In linear programming, we have these ranges. We have ranges that tell us nothing's changing. Okay, and so these sensitivity ranges, or the range in which the basis is unchanged. I'm going to keep using that word. So remember from last lab session, I introduced you to this idea of basis as a name for a corner point. So when you have a large model, it's hard to think of corners because there's so many variables, so many constraints, and so you end up with a basis that could have 5 different constraints binding at once, and so the tradition is to call that basis. It's this fixed value, fixed set of points that generate a potential solution, and evaluation of all the basis points, bases, right? They're called bases. Evaluation of all of those against the objective function tells you which basis is best. Any change in the underlying parameters could cause you to move to a new basis, which means the objective equation or the feasible space changed and caused you to adjust. So we have these ranges, and they're basically saying these are ranges. If you change the right hand side of the calorie constraint from 3 down to 2, you don't generate a new solution, not a new basis. You might generate you'll generate new values for some things, but you won't change the dual variable. You won't change the shadow price. So there could be lots of adjustments, but the same basic solution, the same basis solution, will hold the same requirements. Okay, so on this side we have the variable ranges, and these work with the objective coefficients. So remember the way the Stigler model was set up, all the prices are 1 originally, and so this is saying you need to lower the price of wheat by more than 10% if you want to, or sorry, more than whatever that is, 7% roughly, to generate a new basis. to move away from the current best value for wheat. Yeah, so that's really all we're talking about. So parametric programming says go one step further, and don't just tell me what the range and over which this is unchanged. In fact, go beyond that range and tell me the new solution value, because this sensitivity doesn't tell us what the value is when the calorie constraint drops down to 1.5, and that's something we might be interested in. And it doesn't tell us what the new solution is when the wheat price drops below 0.93. Okay, and so getting those new values and then tracing out how the shadow price on calories changes as we adjust the constraint could be interesting, and we might call that a nutrient supply curve. The supply curve of calories will be larger when the price per unit for calories is larger, and we should be able to trace that out. Okay, so this is mostly what I talked about. So these ranges only give us partial information. We could do a repeated solution method, iterating over multiple values and then tracking those to come up with a parametric program, a relationship between some endogenous variable and some parameter of the model, like a price and like a quantity. Okay. Typically, this is done one parameter at a time, but parameters interact. The dual variables, the shadow values in a model, depend critically on the price assumptions of the model. So if there's something you're paying for or something you're selling and its value changes, its value per unit changes in the objective equation, then the shadow values change. And that's like shifting a demand curve or a supply curve, or it's shifting the parametric program relationship, whatever you've evaluated. So the example would be like if you have a land constraint that you're measuring land demand on, what we did in assignment 4, solve for different values of the land constraint, get the shadow prices, and we might be interested in how does an output price affect, or an output policy that causes 10% increase in the price of corn to change, how does that shift the demand function for land? That might be something that's very important for us to know, especially if we're using these parametric functions, the parametric land demand function, to try to extend some other work, some policy work on, or some kind of policy model. So really, if we're talking about changing two things, the land constraint of the right-hand side of the land and the price of corn, then we are talking about we were already talking about managing several solutions, and now we're talking about doubling that number. So for larger models, it could already take a lot of solutions to span the feasible space. So a good parametric program or a good parametric relationship that we've identified will ensure that all the sort of relevant values have been covered, right? So the relevant range of pricing for some exogenous price, or sort of all the values that might reasonably be considered in the constraint domain should be covered. And so if you have many solutions and you don't know exactly how many solutions, if you need many solutions and you don't know exactly how to define the feasible space, or the domain, I guess. You don't know how to define the domain over which you're going over. Well, a programming environment becomes ideal for that. You just set in the iterations. You set them in based on the quantitative nature of the problem, not based on the range analysis of the sensitivity. Just set up the repeated solutions. Make sure the parameter assumptions are adjusting with whatever frequency you think is best. Collect all the results, and then you can go back and tweak that iterated programming environment as you need to better sort of focus the analysis. Okay, so we have an example that you're going to look through, It's the Stigler Diet model. So the same thing, it's either Lab 2 or Lab 3. I think maybe it's Lab 3 actually. That's what I'm saying in the notes at least. And it's called Diet PP. So this is Diet Parametric Programming 552.gams. You have this file. Uses the same diet model from Lab 3, so you'll have to do the, you have to download the entire package and be sure it's all set up in the same folder. So go back to Lab 3 instructions if you need to see that. But we're going to just implement at the end of that some parametric programming statements at the end of the code, and we're going to look at the calorie supply functions. So what we're going to do as an initial factor, we're going to vary the right-hand side of the calorie constraint. And so in this diet models, when you have a low value for the right-hand side, the constraint is not as constraining or not as binding or not as difficult to meet, and then we'll increment up. And so we'll start from a low value and move it up and make it the demand side for calories larger and larger. And so what we'll really be tracking there is sort of how good are these foods at supplying calories. Okay, and so you'll see that at low calorie requirements you can get very low prices, just like you would expect from a supply side model. And so it's always tricky to think about what you're measuring, supply or demand, but always go with the relationships. We expect this to be a positive relationship as we increase the right hand side of calories more and more. We will get higher shadow prices because the constraint becomes more difficult to meet, more expensive to meet, and that's a supply side problem. That's supplying the calories. You're willing to supply more when they're valued more, and so from a price quantity standpoint, this is a supply side model. And then the second iteration, the second sort of twist to this parametric adjustment we're going to make is what happens when the wheat price changes. So if wheat becomes more expensive, that's going to change the way we view that supply relationship. Okay, so a quick review of the Stigler model in the code. So I've opened my GAMS model here, and everything is going to be the same except for just a couple of changes. So here's, again, this is the Lab 3 model we used. So we are choosing food levels X, so F is the set of foods, and remember we use these include statements to get the sets and the basic data in, and you can see those in the related files. So we need this positive variable for the choice of food quantities, and then the free variable is the objective, that's the cost. We have equations for the nutrient constraints. We have equations, a single equation for the cost constraint, or the cost objective. And then we have the one change we need. So originally when we built this model, we didn't have prices. Everything was fixed so that a serving cost exactly $1 or one price unit. I guess it was, $1. And so if you set the data so that every the units are dollars of food, then you don't need prices. But if we're going to do parametric programming, we actually need the prices. And so I set a parameter here that says the price for foods, and I just set all those prices equal to 1. So PF being assigned a value of 1 is just a vector over all the items in the set of foods, and it says make them all 1, and then we can change those as necessary. So that means we're going to change the objective equation just a little bit. We'll multiply that vector of prices by the vector of quantities to get the cost now. Okay, so let's go back to this, and I just want to remind you that between the model statement and the solve of that first solution back in Lab 3, we put in what we call the options file. and that was just for generating the ranges. And so these ranges that we see here, the sensitivity ranges for equations and variables, they come from including this options file. Okay, so let's move ahead and think about how we would go about modeling our parametric programming statements. And we're going to do it with loops. Okay, and so the loop is what you expect. I think we may have even seen one in a previous lab. It's just a way of running the same programming statements over and over with only one change, or with whatever changes we make in terms of the instructions. So it's a set of instructions to run these statements a set number of times, either until some condition is met or some predetermined number of times. And so we're going with the first one. We're going to create a set, we're going to give it the number of iterations, and then we'll run till we run out of those iterations. The syntax for a loop is just to make a call, right, or the programming function loop. Everything inside of the loop, inside of these parentheses, is part of the loop, and it needs a controlling set. So the loop starts, and it looks and it does the first item in the set, and it runs the programming statements that follow, and makes any assignments, and then it returns. It hits the end of the loop here in the parentheses and returns back, and goes to the second item in the set, second element. Runs through the programming statements, returns until it runs out of, until it hits the last element of the set, and then it exits out, hits this colon, and then moves on to semicolon and moves on. And so we call this the control, right? This thing before the parentheses, the set, is the set that's going to control the loop. Okay, so when you run out of elements in that set, you'll exit out. A loop execution gets done for each value, and then all programming statements will be done for that. And so for our purposes, the loop that we've already seen is pretty straightforward. I'm going to change the right hand side of the calories constraint over and over, and I'm going to collect the right hand side quantity value and the shadow price, and that will give me that supply relationship for calories, right? It's the supply of calories by the set of foods to the diet. But if we want to consider that second element, how does the wheat price affect those supply functions, those calorie supply functions, then we need another loop. And so what we have here is nesting loops. Okay, so it's a nested sort of programming environment where we first loop over something, and then interior to that loop, we're going to loop over something else. Okay, so it's not loop 1 and then do loop 2. It is run loop 1, then run loop 2, then go back, and then run loop 1, and then go back into loop 2 every time. So if you see, you'll hit the first element of this set, run it for every element of set 2, and then when you complete that, you run back out, and then you're to the second element in this set, and then you move into this loop, and you run it for every element in the set. So if this is a 5-element set and this is a 5-element set, element 1, 5 runs, and so you've collected 5 solutions. Back out here, now you're in element 2, 5 runs in set 2, now you have 10 solutions. Element 3, 15, and then so you'll end up with 25. Okay, so the way this works is the loop is entered as one of the if we have loop, the control, and then programming statements, well, loop is just a programming statement itself, and so you can embed it or you can nest it inside of this loop, and it will run all of its loop statements inside of these parentheses. Okay, and so until you run out of those, the interior loop, until you run out of those. You don't go back up here, and then when you run out of these, you can do some additional programming statements or exit the loop. Okay, so the setup here might be clearer with an example, and luckily we're doing an example this time. So what would be sort of the theory here is that we want to run this loop and have it actually control the outside thing, the wheat price, the sort of big picture item. And so give me the first assumption for the wheat price, and so that needs to be set from outside. And we'll have a programming statement here that says, I want to start my calorie constraint at some low value, and then let the loop take over and start adjusting that calorie value. And so it's going to solve for the first calorie value, the second, third, fourth, and fifth, and then we get to the end of set 2 and it'll come back out. It's going to adjust the wheat price again, and then the programming statement here is going to be to reset the calorie level, and then go back into the loop so that we're getting the same set of results out of this loop. The only thing that is changing when we run the loop, this set 2 loop, the interior loop, again, is we've changed the wheat price. Okay, so let's get set up for this. I can tell you I'm going to run the wheat price starting from 50 cents and adjusting it by 20 cents each time. And I'm going to run the calorie constraint 5 times, adjusting it from 1.5 to 3.5, I suppose. Yeah, and so if we're going to run 20-cent iterations on the price of wheat, I want 10 of those. And so these sets, these are set declarations that start right after our solution of the code. And so we're saying these are the iterations over the price of wheat, and I'm just going to call the elements of this set PW1 to PW10. And so something we haven't had is, if you're going to name your set elements the same, give them the same basic name, and only have a suffixed number, then GAMS lets you name all of those at once by using an asterisk. And so writing this statement is equivalent to writing PW1, comma, PW2, comma, PW3, comma. And so it's very common when you're going to have these iterations to just make them some identifier with a number at the end so that you can quickly generate a large number of set elements. We'll do the same thing for the calories, right? So this is the iteration over calories. We're going to do calories 1 to calories 5, and those will be the labels for those set elements. Okay, so we need a parameter that will collect all of our results, and so we're going to make the rows the calorie iterations, the columns the price iterations. Okay, so as we read down, we'll see calorie 1, 2, 3, 4, and 5, and then across will be the changing prices. And then lastly, right before we start into our loop, we need to set the price of wheat at its initial value. Okay, so the core solution, the original solution was $1, or it was solving the price of wheat when it's $1, and we're going to lower that to 50 cents. And then inside the loop, that price will get updated from 50 cents to 70 cents to 90 cents to $1.10, etc. Okay, so once we get that price set to 50 cents, then we can start our loop. So we'll begin the first iteration, and the first iteration, the outer loop, is over the price of wheat. Okay, so it takes its control is ITERPW, that's the set we just made. There's 10 of those. And then inside of that first loop, we need to initiate the starting value for the calorie constraint. It has to be inside of here because we want, every time we run through the interior loop, and we change the price, so we start with 50 cents as the price, and then the next time through we're going to use 70 cents as the price. So when we get back into the second loop for calories, we want it to start at the same place. We don't want it adding on to the last value for the calorie constraint, so we reset it right here. And so this just says every time right before you enter this calorie loop, start at 150, and then you'll make the adjustments inside of that loop. Okay, so we got our first loop. We're going to set the calorie level, the starting value for calories, and then you go inside of the calorie loop. And that's where our solve statement's going to be. So it's going to solve, and that solution will be based on a price of wheat that's set at 50 cents originally, and a calorie right-hand side of 1.5 or 1,500 calories. Solve that model, and then we're going to collect just one thing in this sensitivity matrix, that parameter we made. It's going to be when it's going to be defined over the iterations over calories and the iterations over the price of wheat. It's going to collect one value right now using the current item from this loop and the current item from this loop, right? So these, when you're inside of a loop, you always are being controlled by the set. So we're at the first element of this set, and it's just going to take the marginal from the calorie constraint. So this is how we get it to say NB is an equation, and there's an equation for calories, and it has a marginal value, and that's the shadow price. So NB.M says give me the shadow value for the calorie constraint, write it into the current iteration 1, write it into the current value, and then proceed to the next statement. And the next statement just says whatever the calorie constraint is right now, add 0.5 to the right hand side. And this is an assignment, right? So B calorie should be the old value of B calorie plus 0.5. Then you're at the end of the loop, so you jump back to the top of this loop and you get the second iteration, the second row under the same price. Solves again, gets the marginal value, and so you'll get your second value. Go down here, add another 0.5 to the calorie constraint, hit the end of the loop, so you jump back, you do the third element, and so we're building up the first column under the price of wheat equals 0.5, and we're going to get 5 shadow prices as we run through this loop. So when we get to the fifth one, it'll solve. It'll get to the end of this, and it'll add something to the calorie constraint, but it won't solve again. And it hits the end of the loop. So we just ran the fifth iteration. We hit the end of this loop, and there's no more controls. The set is empty. There's no remaining elements to iterate over. So it exits this loop, and we have a programming statement, our assignment here that says, okay, the price of wheat is currently 50 cents. Add 20 to it. Let that be the new price of wheat. And then you hit the boundary of this first loop, and you jump back up here. Okay, and so we get down here, 50 cents plus 20 is 70 cents. Hit the loop, go check, and we do have a second iteration, a second element here, the price in this price set. So now we have a price of 70 cents, and we begin through the second loop of this outer loop, or the second iteration of this outer loop. Reset the calorie constraint from 1.5, from whatever value it was, we're going back to 1.5, and then enter this second loop again. Run it 5 times. When you hit the end, you'll jump out, you'll change the price from 70 to 90 cents. Hit this, and it tells you to go back. Reset the calorie constraint, run it 5 times, $1.10, okay? And so you run through all that, and then the last statement is just display the sensitivity matrix. Okay, so I have the GAMS code here. Everything is in order, everything's just like it was, and this is the exact code that you have. So click on run, and yeah, it has to run a few times, right? There's 50 solutions it needs to generate. It's going to, for 10 different prices, it's going to run 5 different iterations of the calories constraint. And it's not going to take long, but it has to go through and do all that running and writing and so forth. So it gets to the end, go straight to your display. Right? If you want to do analysis, of any of these solutions, you should have collected the values or run those specific ones. Go straight to the sensitivity matrix. And here's what we have. At a very low price, the calorie constraint, a low price for wheat, the calorie constraint's not binding, you end up with these zero shadow prices, and then you start at higher calorie constraint values, you start generating those shadow prices. And so our first supply function only has a couple of different points at the higher calorie values, and as you move on, you see that you get a full price system, or a full sort of set of prices here between 1,500 and 3,500 calories. So 7 cents, and then it gets stuck at 11 cents until the calorie constraint gets very large. And then the price jumps up to 0.023, 0.024. And so as you're looking across these, you see it sort of flattens at 0.024. And so for the, if you were thinking of tweaking this, you might think of running the calorie constraint even higher. Of course, you run a risk of generating infeasibility in this, and that of course is something you have to check for. If this exits out for an infeasible solution, you have to go back and make some tweaks. But the real issue here is 3,500 calories is really at the upper range of what we want to be, of what we would be interested in. So from an economic standpoint, sort of diets that range between 1,500 and 3,500 calories are the most interesting. And we've covered those, and we've also covered sort of the beyond the interesting range of price for servings. We've taken the price cut by 50% and increased it by 50 plus, and doubled it, more than doubled the price. So we're well beyond that. And so, looking here, you see what it looks like to shift the supply function. So the initial point is the same, but in this sort of middle range, the supply function shifts up when the price of wheat goes up. It shifts up when the price of wheat goes up. It shifts up when the price of wheat goes up. So the one thing we might consider, is tracking that, or tracking even a third price. If we've sort of zoned in on what the sensible range is here. But anyway, that's what we're doing, right? That's what we're trying to uncover here, is how dependent are these supply functions for calories on the price of wheat, which is sort of more responsive. And so you see that there's this sort of flat range of the calorie constraint that's consistent, but what's kind of interesting is it's very responsive to the price of wheat here, that shadow value is, okay, until it's not. At very high wheat prices, it doesn't change much because, well, you can probably imagine wheat has been substituted out as much as possible here, right, in these later values. And so you could go back and investigate all these different solutions, and what you should see is at low prices for wheat, you're using a lot of it and you're getting cheap calories out of wheat. As the price of wheat gets expensive, you start to shift away from it, and the price of wheat gets too large and the calorie constraint is no longer, the calorie supply function is no longer responding to it. Right? So we're out of the range right here. So this is the last change we make. And so, that has implications for the dependency of wheat demand by the consumer on its ability to supply calories, because if it was more efficient at providing calories, it might survive longer in this solution, even at the higher prices. So that's really what we've been after here, is sort of getting some of this parametric programming type analysis out of what we've done. With that, here's the actual collection of those results. With that, I'll leave you with to run this and to go to the quiz for this lab and investigate this a little bit more using the solution we just ran.